Okay, then shall we start? So good afternoon, everybody. So welcome to the Weekend AIP Young Scientist Seminar Series, but done in University of Tokyo today. So my name is Masashi Sugiyama. I'm chairing the session today. So today's guest speaker is Wei-Fa Fu from Stanford University, and he graduated from University of Tokyo 4 years ago in the master's program in our lab, Sugiyama lab. Then he has been a PhD student in Stanford, and you have already graduated officially?
This quarter.
This quarter.
Yeah.
Great. So then he will be talking about on the predictive power of graph neural networks. This is really a hot topic. We are very much excited to hear his talk. Okay, please start.
Okay, thank you so much, Professor Sugiyama. Thank you for the kind introduction. And
but if you have any questions, please speak out or write it in the chat window.
Yeah, sounds good. My talk will be around the 45 minutes, so I'm happy to answer any questions at the end. So today I'm going to talk about the predictive power of graph neural networks. So I'd like to start my talk by saying,
I don't mind if you leave your I think speakers should be fine. Okay. Otherwise, it's not easy to speak.
Okay, sounds good. Thank you. So I'd like to start my talk by saying that graph structure data is everywhere. Many real-world objects can be naturally represented as graphs. For instance, the molecular graphs, social networks, knowledge graphs, citation networks, biological networks, and so on and so forth. And we're interested in performing machine learning tasks over this kind of graph structure data, such as predicting the property of this molecular graphs, predicting new friendship in social network, which can be cast as a link prediction between two users, completing missing facts in the knowledge graph, predicting some subject areas of paper in the paper citation network, and so on. And in order to perform all these machine learning tasks, we need to have a good feature representation of graph. So the conventional approach to this is the feature engineering on graphs. For example, to obtain a feature on nodes, we can use a node degrees, personalized PageRank, graphlet, and so on. For link prediction, we need to have a good feature between a pair of nodes. And for this, people have developed a variety of similarity metrics like a common neighborhood, Jaccard coefficient, other atomic R, and so on. And for making comparison between graphs or making prediction at the level of the entire graph, like predicting the property of molecules, people have developed a variety of graph kernels, like random walk graph kernel, shortest path graph kernel, so on and so forth. However, these approaches do allow us to make a prediction over graphs. The issue here is that this approach requires manual efforts on feature engineering, and as a result, this often gives us a suboptimal performance because maybe it's really hard and time-consuming to find the optimal feature for the given task. So recently, what is getting a lot of attention is a deep learning approach. Especially here, I'm going to focus on the graph neural networks, which are a class of deep learning models for making prediction over graph. And I'm going to introduce GNN later, but there's no need for feature engineering in this GNN approach. And these graph neural networks provide promising results on many application tasks, like a variety of node classification, link prediction, graph classification tasks. And even in the academic community, there's been increasing research on graph neural networks. So here I'm showing you the IQ keyword growth from 2018 to 2020. And you can see that at the top, you can see this GNNs. There have been increasing number of papers that use this keyword GNNs. There's more and more papers on graph neural networks from academia. So even before the start of my PhD, many graph neural network models architecture has been proposed. Some representative models are shown here, like a graph convolution network, graph sage, message passing neural network, graph attention network, so on and so forth. However, despite a lot of advances in models, these GNN models have been developed on small and unrealistic graph benchmarks. For example, these models networks have been developed on this Cora data, which is a citation network with only 3,000 nodes. And in the graph classification data sets, the most representative one is a MUTAC data set, which is just a set of 200 molecular graphs. And you can see that these are too small for us to develop meaningful deep learning models. And And this small benchmark do not really reflect the real world prediction task that we are interested in the real world. And moreover, we've seen a lot of GNN models, but these architecture designs have been really ad hoc, and there hasn't been principled guidelines to design different GNN models. And as a result, the issues of the small benchmark and this ad hoc design of the GNN model architecture so far have been limiting us from building powerful predictive GNN models for real-world tasks. So in this talk, our goal is to build powerful graph neural network models for making prediction over graph structure data. To start, I'm going to first provide an understanding on the predictive power of GNNs. So there are a lot of variants, but we want to understand all these variants under a single framework, which gives us this principled guidelines for designing new GNN models that are more powerful than the existing ones. In part 2, I'm going to talk about how to improve the predictive power, especially how to improve the predictive power of GNNs in the unseen data scenario, how to improve the generalization power of GNNs. And I'm going to specifically focus on the low data regime that are prevalent in the real world. And finally, to resolve the issue of the small benchmark, I'm going to develop data sets to benchmark the predictive power of graph neural networks. So the outlines here, we're going to focus on the predictive power of GNN. We're going to understand, improve, and benchmark the predictive power of graph neural networks. But before that, let me first talk about the preliminaries of GNNs to make sure that everyone is on the same page. So the preliminary GNN, formally we're given this graph G with a set of vertices V and the set of edges E connecting these vertices. And each node has some input feature X of V. And as an input layer, we're given some this input feature associated with each node. And for the subsequent layer, what GNN does is iterative message passing, iterative neighbor aggregation. So what this means is that we gather the embeddings of the neighboring nodes from the previous layer here. We're going to aggregate the embeddings and combine the embedding with the node of the embedding of the node V itself from the previous layer to get the embedding of the node V at the current layer. We do this iteratively for L equals 1 to the capital L to get the embedding of the final layer. Now, what are the properties of this combine and aggregation function? So for aggregation function, we're going to use this permutation invariant neural networks. And this permutation invariance is important because when you aggregate the neighbors, if you think about graph, there's no canonical ordering of your neighboring nodes. So this the output of this aggregation function should be insensitive to how we order the inputs. And some examples are like GCN use this average based aggregation. So average the input feature, apply linear function followed by radial activation. This graph stage use a max pooling based aggregation function. And you can see that both of them are permutation invariant, doesn't depend on the input order. And for the combine function, we typically concatenate these two embeddings, the embedding of node V and the aggregated embedding, or we typically just do the weighted sum of these two embeddings. So combine is relatively straightforward, while aggregation is more interesting because it takes a set of inputs as input. So to complete the picture, once we get the embedding of the final layer, how do we make prediction? For the node level prediction, we usually apply some prediction head MLP, multi-layer perceptron, on the last layer's node embedding to make, for example, predict some classes on the nodes. For the edge level prediction, we typically, for example, take the inner product between the last layer node embeddings to predict the score between pair of nodes. And for the graph level prediction, we first use the permutation invariant function to pool the embedding of the node within a graph, then apply some MLP on top of the pooled embedding. And so you can see GNN can be used to make variety of prediction for graph. Yes.
Could you please provide some practical examples for these three prediction tasks?
Yeah, so great question. So for node level, you can think of, for example, predicting the subject area of papers in the paper citation network. That's a kind of node level prediction. For edge level prediction, you can think of recommending new friendship in social network. And for graph level, it's predicting the property of molecules.
Thank you so much.
Yes, great question. So given this, now I'm going to first provide the understanding on the predictive power of GNNs that I just introduced. So as I said before, many GNN models have been developed. And what's interesting is that all these models are following this combine and aggregation framework that I just introduced before. However, as I just said, this GNN design had been ad hoc, meaning that the design of this aggregation combine function have been basically based on empirical trial and error, and there's no kind of principles in designing different GNN, different aggregation models. And therefore, we need a principle framework to understand and design GNN models. And specifically here, we're going to focus on understanding the expressive power of GNNs. So expressive power is a fundamental kind of ability in machine learning model. In machine learning, we're interested in learning some ground truth underlying function from data. And this expressiveness is about whether your class of models is expressive enough to include this ground truth function of interest or not. So this, and you can see this is a kind of prerequisite of building powerful predictive models over graphs. So specifically, we ask this question: what kind of functions over graph can L layer GNN express? And our key insight is that this L layer GNN use the last layer node embedding L sub B L, this last layer L embedding to make prediction over nodes. And the expressive power of GNN, therefore, can be cast as a discriminative power of GNN. If GNN can, embed two nodes into different embedding at the final layer, then by applying some prediction here like MLP on top of it, it can certainly express some function that outputs different values on the different nodes. And so the key question that we're going to answer is what graph structure can this last layer node embedding distinguish? And a key concept to answer this question is the computational graph for node B. So I'm going to talk about the computational graph. Computational graph basically illustrates how GNN compute the node embedding of the particular node B. For example, let's think about this example, how two-layer GNN generates embedding of node 1. And from now on, we use the color of this vector to denote the difference in the input node feature. And here, for example, we are focusing on uniform node feature. So we are purely focusing on the graph structure from now on. But our argument can hold for different input node feature. Okay, so how do we generate the embedding of node 1 in this input graph? So we go from the output to the input. So to generate the embedding of the node 1 in the second layer, what we're going to do is we need to aggregate the embedding of the neighboring nodes 2, 3, and 4 from the previous layer 1, right? So this can be illustrated in this computational graph. Then recursively to generate the embedding of the node 2 in the first layer, we need to aggregate the embedding of the node 1 and 3 from the previous layer. And at this point, we hit the input feature. And we do the same thing for node 3 and 4. So this gives us a complete picture of how this two-layer GNN generate the embedding of node 1, right? And what we find here is that if we, draw this computational graph for all the nodes in the graph, you can see that this computational graphs is really kind of capture the local neighborhood around each node. And this local neighborhood, this, if you look at this structure of the computational graph, it follows the rooted subtree structure around each node. So from here, what we can say is that if two nodes have exactly the same rooted subtree structure, then the GNN would output exactly the same node embedding, because this for node 2 and 3, we're going to use exactly the same computational graph with exactly the same input. So there's no way we can map them into the same embedding, different embedding. So for node 2 and 3, GNN would map them into different into the same embedding. And you can see, from this figure that node 2 and 3 are kind of symmetrically positioned within this graph. So it kind of makes sense to map them into the same embedding. On the other hand, if these different nodes have a different rooted subtree structure, we want the maximally expressive GNN to map them into different embeddings. So ideally, if these computational graphs are the same, we want the expressive GNN to have a output different embeddings if the computational graphs are different. And this property is what we call injective. So mapping from a different computational graph into different embeddings. Now, how can we achieve the injectivity of this computational graph? It turns out that if we make sure that this mapping is injected at each layer of the GNN, then we can ensure the entire GNN is injected. This is because in the first layer, we kind of maintain all the information about input, and we can pass it to into the next layer, which again, retain all the information. Therefore, the entire mapping you can see it's kind of becomes injective. And therefore, what this picture shows is that the expressive power of this multi-layer GNNs can be characterized as the expressive power of the neighbor aggregation, basically a single step. The expressive power of this entire thing, complex thing, can be cast as just a single step on neighbor aggregation, right? And if you think about this, what this single step neighbor aggregation does is basically can be mathematically characterized as a multi-set function, permutation invariant function over a multi-set. And here by multi-set, I mean we allow the multiplicity of elements. So here we can allow the colors to be repeating in this set. So what this means is that the expressive power of GNN can be characterized as the expressive power of the multi-set function that GNN use for this aggregation function. Now, this kind of framework can be used to analyze GNN with different multi-set function, like all the GNNs that have been developed so far. For case study, I'm going to illustrate the two examples of how we can apply our theoretical framework to analyze the expressive power of GNNs. Yes.
So to represent this graph, we need like a 4 unique network to represent this graph, or just one network. I mean, for that example, it's 4 nodes. I want to ask if we need 4 unique network to represent this graph.
Okay, so 4 unique network.
Yeah.
What do you mean by a network?
I mean, like in the implementation, like for PyTorch network or TensorFlow network to represent this graph.
I see. So
Because
this graph is just a graph with 4 nodes, and what GNN does is like basically at each layer, this gray boxes are all just a multi-set function. So we implement with some multi-set function with PyTorch. And then in the second layer, we can use different multi-set function. And for each, if we want to generate embedding of node 1, we're going to call this a multi-set function in the first layer, then the multi-set function in the second layer to generate the embedding. Okay.
So this is learning the parameters for the multi-set.
Yes.
I see.
So for example, I think I have the GCN. Sorry, let me see if I can find it. GCN is a mean followed by linear followed by ReLU, so you can learn the linear part in the multi-set.
Thank you so much.
Can I ask a question?
Yes.
I have been wanting to ask this question for a long time. Like, if you want to understand the expressive power of the graphs, it seems like you don't need to understand the expressive power of stat functions, aggregator. For example, if we want to study a problem where the node feature is the median of the neighbors,
Okay.
can you learn that based on a network, a GNN with mean and or max?
I see. For median,
Yes.
I guess median operation, my intuition is that it's pretty different from sum aggregation. But I'm going to show that if you use sum aggregation, you can learn the parameter in such a way that it perfectly mimics the median aggregation.
Precisely.
Precisely, yeah.
All right.
I'm going to show the proof later.
Okay.
But they're meant, yeah. So I'm going to show the proof later.
Okay.
How we can, use some aggregation to model any function, including median aggregation of any function.
Thank you.
But there definitely needs some mathematical assumptions. So I'm also going to talk about that in the proof.
Thank you.
Okay. So let me show this, apply our theoretical frame to GCN first. So just to remind you that the GCN use this aggregation function, first average the multi-set of the input, followed by a linear function in ReLU activation. And it turns out that GCN, this mean-based aggregation, fails to distinguish multi-set with the same proportion of elements. And this is because if you average this different colors, if the different multi-set have the same proportion, then you can imagine, averaging them will give you the same output. So this basically means that this GCN cannot distinguish this kind of different multi-set neighborhood. Okay, so what about the graph stage? So graph stage use this max pooling based aggregation. And what you can show is that the graph stage fails to distinguish multi-set with distinct elements. And this is because, for example, if you consider adding the same element on, for example, adding gray color on top of this color, even if you think about the result of max pooling, even as long as the added color is already in the same set, the output wouldn't change. So this example shows that this max pooling fails to distinguish this multi-set with distinct elements. And therefore, this graph stage is not injective and less powerful than GCN, because GCN at least can distinguish these two with a different proportion, but the graph stage cannot. Okay, so now I'm going to introduce our own model called graph isomorphism test network, and this is a maximally powerful injective multi-set function. So the architecture here is we first apply some MLP, followed by some aggregation, and followed by another MLP. And here we can actually see that by using this sum aggregation, it doesn't suffer from the limitation of the max pooling, mean pooling that I just introduced before. And theoretically, we can show this multi-set function can model any injective multi-set function. And I'm going to show the proof intuition now. And this might answer your question. So let's consider, distinguishing these three different multi-sets. And let's assume each color has a bounded multiplicity. So this means that, if we have for different multi-set, let's say we won't have more than 10 repeating colors. So we won't have 10 gray colors and 10 green colors. This is the assumption that we need to make. And this can be arbitrary, like 100 is fine, but let's just assume for 10 now. And we construct the first MLP such that we map each color into this kind of digit in this way. So the mapping the green color into 0.1 and the green color to 0.01. If we have another color, we can map it to 0.001 and so on and so forth. Then if we sum these embeddings, we're going to obtain this one for different multi-set. And what we see is that we can read off the count of the input color by looking at the digit. So the first digit corresponds to the number of gray colors in the input, and the second digit corresponds to the number of the green colors in it. And by applying another MLP, we can see that this entire multi-set function can model any injective multi-set. So back to your question, maybe you want to model some median-based aggregation function, right? That by using this part, you can map, any injecting different multi-set into different embedding. And by using this universal approximation theorem of the second MLP, you can somehow mimic the median kind of function. But of course, this requires this one to be universal approximator, and maybe we need to assume this bounded multiplicity. And maybe if you have so many colors, you have 0.00001, so many, you kind of need to have an infinite precision, machine precision here. So there are a lot of limitations, but mathematically, if you can assume this, and if you can have an infinite machine precision, you're able to model any injective multi-set function.
Well, the sum is not injective. Right?
Oh, sum is injective because by adding them together, you're essentially counting different colors. So
like we can create a set with different, with the same sum but a different median.
what do you mean?
Like we have a set A and set B,
Yes.
and they have both the same sum, but
Yeah.
their median are different.
No. No, I think the median is always less explicit. For example, like because the sum is essentially you can think of sum as counting the colors. So whenever the inputs are different, your output will be always different. But if you think of a median, maybe your input is 1, 2, 3, the median is 2. Another input is like 0, 2, 4, median is again 2. So you do have these two multi-sets that are different, but that are mapped into the same median. Maybe we can chat offline.
Thank you.
But the key message is that by using sum, we're essentially counting different colors. Okay, so this kind of explains this MLP, sum MLP, this kind of entire architecture gives us a very powerful in our multi-set function. Now, I'm also going to talk about, what about, GNN with a less powerful aggregation function. And this, I argue that they are still really useful in practice because a lot of application actually offers very rich input feature. For example, think about node classification in a citation network. Each node is a paper here, and each node is kind of can be represented as a textual feature, like a bird feature. In this case, every node is likely to have different features, right? So in this case, the sum or max pooling or mean pooling, they can all distinguish different multi-set because the features are different. In this case, mean or max aggregation can also be expressive, and different aggregation function can now bring different inductive bias. For example, the max pooling might be selectively, choose the neighborhood, or while sum pooling tend to count the number of neighborhoods, mean pooling tend to kind of smoothing out the input feature. So really different aggregation function have different inductive bias, and the choice of this aggregation function is more of empirical trial and error. So just to finally provide you the guideline, for designing GNN. So the first case one, when node features are not so rich. And for example, in molecular graphs where a lot of nodes are just carbons. In this case, we want to design a GNN with a very injective, powerful multi-set function based on, for example, summation. In case two, where graphs have a very rich node feature, like a text feature, then we probably want to design GNN with multi-set with a appropriate inductive bias. So finally, I'm going to talk about the impact of this work. So, this work was published like 4 years ago, and it's received 3,000 Google Scholar citations. And many GNN models have been developed and analyzed under our framework. And many follow-up works on designing and improving the expressive power of GNNs has been done, and they are basically do this by expanding the class of GNN models. For example, by allowing some inputs to be given to the GNN. For example, for example, some GNN give the cycle counting or this kind of auxiliary graph structure information as an input to GNN, which help improve the expressiveness. And the summation-based gene model serves as a strong baseline for graph classification. We're very
That means gene is already expressive, but still other people propose different structure.
yes,
I try to show that the new ones are better than gene in practice.
right. So gene is most expressive within the class of this combine and aggregation function. But then people have extended this framework by allowing, like, for example, counting the cycle of this node in which this node is in, and use that as auxiliary information. Those kind of input really helps GNN models. I see, distinguish different graph structure. So to be more precise, gene is most expressive within that class, but you can always expand the class to improve the expressiveness.
But in standard deep learning, people prefer so-called over-parameterized models.
Yes.
Can you think of a kind of similar
Mhm.
like concept in GNN?
Right. So I think over-parameterization here. So I think here the expressive power of GNN is more of a, the difference in computational graphs. By over-parameterization, I feel like it's more of like how many hidden units we use for the gray box part. So I feel like there are a bit different concepts. Right? And for GNN, people definitely find it's easier to kind of use larger hidden dimensionality. But even if we use larger hidden dimensionality, if we use max aggregation, we can never fit the
Right.
I have a question.
Yeah.
You say the gene use the map as the aggregation function.
Gene,
Oh, no, gene use the
Sum.
sum.
Yes,
Sorry,
yes.
sum.
Yeah.
So for the task like graph classification,
Yeah.
if a graph with few nodes, there are few neighbors, but while other graph has many nodes
Yeah.
and many neighbors.
right.
So some output may be small, but some output may be
Mhm.
very large.
Right.
So does the gene will met some training difficulty in practice?
That's a great question. I think in those kind of social network, gene may not necessarily perform well. It kind of, for example, you might output very large value for celebrity nodes or paper with a huge number of citations, while out the small value. But in practice, the inductive bias we want for making prediction on, for example, social network is that if two nodes are similar, are nearby in the graph, you want to make the same prediction, right? So I would say, gene may not have a best inductive bias for social network kind of problem where you want to make similar prediction for nearby. Yeah. But maybe if your prediction task is about predicting the popularity of the nodes, then I would say gene has a good inductive bias. But if your output target label is predicting, I don't know, category of the nodes, like then G doesn't have.
Depends.
Depends on the target label. Yeah.
Thank you.
Great question.
Sorry, we have a question in the chat box.
Oh, what's the question? Can you read it out?
Yeah, but I don't know which slide it is. For the third case, if there is 10 green color, then the sum result
yeah.
will be 0.1.
Yeah.
It seems
Yeah.
cannot reflect the counting or the
Yeah.
different digits.
That's a great question, and that's why we need this bounded multiplicity of the elements. So we assume if this is, for example, 100, then we can map this into 0.1, this into 0.001. So there's no conflict between different colors. So here I'm just assuming for simplicity, you know, the bounded multiplicity is bounded by 10. So there's no such conflict in this example. Great question. Okay, now let's move on to the part 2, improving the predicted power. So far what we did is to design this expressive GNN, whose hypothesis class is expressive enough to hopefully cover this ground truth function. In practice, we all know that expressiveness alone is not enough. It's more of a prerequisite to build useful machine learning model. In practice, what we need to do is to, given this hypothesis class, we need to learn a GNN model from data such that this learn function is close to this ground truth function, which means that this learn function has high generalization power. And this is especially challenging under limited data scenario. And here I'm going to talk about two challenging scenarios: limited label data and limited edge connectivity. And we're going to talk about how we can learn good green this learn function from limited data. The first scenario we're going to consider is the limited label data scenario. So the motivating application here is the GNN applied for molecular property prediction. So given this molecular graph, we want to judge if it's, for example, toxic or not. And for this kind of a task, we know that task-specific label data is really expensive to obtain. For each different toxicity type, we need to gather training data, train the model, and the test performance. And this training data is really expensive. So our approach is pre-training. Basically inspired by the success of BERT in natural language processing. So in practice, in chemistry domain, we have abundant unlabeled data and abundant task relevant labeled data. So we, outside of this specific task, we do have a lot of data out there. So our key idea is to pre-train this GNN to inject as much domain knowledge as possible into the GNN. And such GNN can be fine-tuned on, variety of downstream tasks with limited task-specific label data to improve the generalization performance on this small data set. The open problem here is that basically no one has considered this a pre-training GNN before, prior to our work. So what is the really effective pre-training strategy for GNN? This is a kind of open problem. So our key insight here is that we find it really effective to not only pre-train at the level of this entire graph. So GNN obtain the embedding of the entire graph by first, obtain the node embedding and then pull it to obtain the graph embedding. And not only, we want to obtain a pre-train at the level of the entire graph, but we also want to consider some self-supervised learning at the level of the individual nodes, so that, in some sense, this if you think about the natural language, you want the word embedding to be high quality, not just sentence embedding. So we want the embedding to be high quality, both at the level of individual nodes as well as the level of the entire graph. And due to the time constraint, I'm not going to talk about the self-supervised method that we developed, but what we can show empirically is that really by having both graph level and node level pre-training, we can significantly improve the performance over non-pre-trained GNN. So this purple line is a non-pre-trained GNN model, and we test the performance on the 8 different downstream molecular property prediction data sets. And you can see, this is really above this non-pre-trained GNN, while if we just perform the graph level pre-training, it's typically much worse than in the green line. And on some data sets, it even performed worse than the non-pre-trained baseline, which basically means that this is a negative transfer on some data sets. So what we find is that having pre-training at both local level and global level is a really important strategy.
And these downstream tasks are graph level or node level?
Graph level.
Okay.
And only graph level. So our pre-training task is like we make prediction over like 1,000 different molecule labels, and our downstream like task is a really small data set over 8 different labels. And yeah, it's interesting to find, like, we initially tried this, but find this only graph level approach doesn't really work. So develop this at this node level pre-training strategy, which improves the performance. And just having node level also doesn't work, although I didn't show it in the performance here. Okay, so
But apart from the model structure, can you simply apply like standard transfer learning technique or weakly supervised learning technique here? Like PU learning, for example, like when you train GNN.
I think we can. So for transfer, so yeah, well, what
So simply losses change. So in transfer learning,
Yes.
with supervised learning.
yes. I guess in a lot of transfer learning, like what kind of I think some transfer learning,
Yeah, okay. So some methods are maybe very specific to certain,
right,
architecture, but generally we have some importance weighting that domain matching.
right. Oh, I see. Right. I think for those importance reweighting, we need to have this target label to kind of have kind of correspondence to the downstream label, which may not always be the case. Right? I'm sure like a lot of, for example, multitask learning, doing multitask between this and all the downstream tasks can improve performance. But some kind of domain adaptation requires the target label to be shared between the training time and test time. So that may not be whole in practice. Okay, let's move on. So so now let's talk about another kind of limited data scenario, which is limited edge connectivity. So the motivating application here is that social networks or recommender system where this kind of real world graphs follow power law degree distribution, meaning that a lot of nodes have a very small number of neighbors, and only small number of nodes have a very large number of neighbors. Think about the kind of celebrity nodes in the social network. There are some small number of celebrity nodes with huge number of neighbors, but a lot of nodes probably don't have a lot of followers, right? So this kind of power law degree distribution is really prevalent in the real world. And if we train GNN on top of this real world graphs with power law degree distribution, we typically find GNN underperform on tail nodes, basically the nodes with small number of degrees. And this is surprising because we do find there are a lot of tail nodes in the real world, but even if there are a lot of nodes, GNN still perform really work badly on tail nodes. So here's the performance. X-axis is the node degree, y-axis is accuracy on that specific degree. And you can see that when the node degree is small, really the GNN perform really badly compared to the node degree is large. Right? So what we see is that these tail nodes are much harder than head nodes for GNN to make accurate prediction And this is probably because GNN can gather small number of evidence for the kernels. So how can we tackle this prevalent problem? So our method is called tune-up, and our key insight is really simple. So what we notice is that we have this head nodes in the graph with a lot of edge connectivity. If we simply drop edges from the head nodes, we arrive at the tail nodes with a limited connectivity. So in some sense, we can do a lot of data augmentation. We can generate much more number of tail nodes just by dropping edges from the head nodes.
Doesn't that change the distribution of the graphs?
Yes, it will change the distribution of the graph. But if you think about locally, you have a more tail nodes. Of course, you have a less head nodes here. So in that sense, the distribution is changed. But as I'm going to show later, actually performing well on head nodes is super easy. So it's better to focus on the head nodes. And actually that question leads to this curriculum learning that we developed. So what we do is that we initially train our GNN on the full graph to make sure this base GNN performs well on the easy head nodes. So we train GNN on this entire graph, and in the second stage, we fine-tune this GNN on the hard tail nodes by dropping edges from the head nodes. So we kind of go from the hard, easy to hard. It's kind of a curriculum. Let me talk a bit more about the second stage because it's interesting, like how we synthesize the tail nodes. So let's think about the link prediction, where we usually have the input to GNN is this kind of input graph, and we want to predict these are 4 links on this node, right? So the way we synthesize tail nodes is really simple. So we just drop the edges from the input, and the target supervision can be reused. So what now GNN sees is a sparsified graph, but we force GNN to still predict these 4 links attached to this node. And this way we can kind of create the input-output pair for the tail nodes.
Like a dropout.
It's kind of a drop edge. Also, dropout drop the hidden units. Drop edge drop the edge. Yeah, there's a technical drop edge, and we actually just adopt. Yeah, and for the semi-super and node classification, it's more challenging because if you think about this graph, semi-super node classification, you're given small number of labeled nodes, and a lot of nodes are unlabeled, and for this head nodes, it can be the case that this head node is unlabeled. So if you naively adopt the strategy, you don't have any target label to reuse. So what we do is quite simple. We use the base GNN that we obtained the first stage, and then we use the base GNN to predict the pseudo label. So let's say this base GNN gives predict the pseudo label 0, and this may not be perfectly accurate, but we still predict it. And this predicted pseudo label can be reused at this stage, right? And so what's this interesting here is that we're using less information as input to recover the prediction that's made based on the full graph. And this strategy turns out to be super useful. So our tune-up is quite simple. In the first stage, we just train the GNN on the original graph, which has been done before. If we are focusing on semi-supervised nodes classification, we're going to predict the pseudo labels using the base GNN. And in the second stage, we're going to fine-tune this base GNN on the sparsified graph. And this gives us the tune-up. And turns out that this gives us a very significant improvement over a wide range of settings. So we have for example, we tested this graph stage model on this semi-supervised node classification setting, and we find that this tune-up, which is on this orange line, is better than base GNN on every node degree, but the improvement is really large, especially when the node degree is small. So the tail node performance improvement is really huge. And we also test the performance on leak prediction recommender system. We again see this huge improvement of this tune up. And we also try different GNN architecture, and we see this consistent improvement. So we find this training strategy to be useful across different tasks, across the different GNN architectures. And so it's quite exciting method, very general and exciting method. And we also did this evaluation study where we tune up has a two-stage training. What if we remove the second stage? What if we remove the first stage? What if we remove the pseudo label? We kind of show this each of the component is necessary for our method to achieve the maximum performance.
I have a question.
Yeah.
On the stage 2.
Yeah.
So how to generate this random age class
Oh, we just drop alpha percent of the age.
randomly?
Yeah. And alpha is a hyperparameter, so we tune it from 25, 50, and 75%. Yeah, it's a hyperparameter we need to tune. But we have the validations. So
because recently I have read some papers about recurrent learning. They use the RL reinforcement learning process
I see.
to choose what part of data you need to train first and what part of data you need to train later. And I think maybe they can have some connections.
Right. Yeah, that's a great point. I think the currently our method is super simple. So definitely how we, this drop edge strategy, better drop edge strategy can be developed to improve the nice. Thank you. Okay.
Sorry, can I turn to the last page, 47. This page, this page. So I have a question. I find the improvement for example, for the left upper figure, if the node degree is small, the
Yeah.
improvement is larger. But for some cases,
Yeah.
why is the media?
This one?
Yeah, like this one.
Yeah.
If some node degree is small, but the improvement is also
Yeah.
little.
I think that's a great question. I think for this case, maybe basically this part is when the node doesn't have any edge. And it looks like this part is almost impossible to make any accurate prediction. So it's bad on both tune-up and base GNN. It's just the evidence is too small to make any accurate
Another
prediction.
question is, you drop some edge randomly,
Yeah.
so that the hyperparameter, the drop proportion.
Yeah.
So does this figure will change if you change the drop ratio?
So I picked the best alpha. I picked the best drop edge ratio.
Oh, okay.
Based on validation. Yeah. It's
I was wondering if the sparsity of the graph has any effect on the representation power of the graph neural networks. Like, I thought that if the graph is more dense, then it should have more, the hypothesis space should be larger, or is it the same?
That's a good point. I think for the expressiveness of GNN, maybe if the graph is, how to say, that's basically the dense graph or specified graph. I don't know like which one requires more, expressive function. It really depends on the target label that you want to model. But maybe on some dense graph that the different nodes tend to have very different node degrees. In that case, maybe it's easier to make different prediction by some base GNN, for example.
I thought that if like,
What do you mean? Yep.
if the density, if we can like, if less sparsity leads to higher expressiveness, then why don't we just like connect every nodes together and make it a complete graph.
Oh, I see.
Yeah, and then learn something.
If you you can add pseudo edge, but how to say, you can kind of imagine the added pseudo edge doesn't really improve the expressiveness because those pseudo edge cannot be distinguished. If you can have a two like a you can have graph, but you can connect this nodes to all the other nodes, but this nodes to all the other nodes, but still each node has, for example, how to say, you basically just add this pseudo edge when new two nodes are not connected. That doesn't really improve the expressiveness. If you look at the local neighborhood, you kind of just have a different edge type. So this nodes may have a degree of 1, and if you add pseudo edge, this may have a degree of I don't know, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 7, right? But how to say, basically pseudo edge just doesn't provide any additional information about the graph structure. If you just add the complete edge connectivity, you can do that, but does that add any sparsity or like a graph structure information? Not necessarily. Yeah, because you are not really adding any information. You're just connecting all the nodes together, right? That shouldn't really add any additional information. Unless you add the edges in a more clever way, maybe that can improve the expressiveness. But if you just connect all the nodes, that doesn't really add the additional information. If you connect the edges, if it's a 2 hop away or do that kind of clever trick, maybe that can improve the expressiveness. But if you simply connect all the nodes in a pairwise manner, I don't think that gives you more expressiveness. Yeah. But maybe I'm wrong, but we need to think more.
I have another question about the last question, like the added pseudo edge, like if we added pseudo edge, we can think that the distribution will change greatly, but if we like uniformly randomly throw out the edge, the original distribution won't change so much.
Yeah.
Like, so the added the pseudo edge will actually decrease the performance. If you that you was wondering.
Add the edge will decrease the performance.
Yes, added pseudo edge because theoretically, like if we drop some edge, and if we do some inverse function like add some edge, they are the same.
Yeah.
But if we add just add a pseudo edge, it will greatly change the distribution.
Right.
So if it won't work, I don't know if it is.
So you are proposing instead of removing edges, you add the edge.
Yes.
You said it doesn't work.
Yes, I was wondering.
I haven't tried adding edges, but I definitely agree. Like adding edges is more challenging. Just removing edges is easier, right?
Yeah.
Because we're just we know all the edges are true, and we are removing this edge and simulate the simulating this tail nodes, right? But the adding edges, so basically adding edges to turn the tail nodes into head nodes, I think is more challenging because it's basically solving the link prediction problem, which itself is super challenging. So, so I think that approach, I don't know, I haven't tried, but maybe hard. Yeah, turning the head nodes into tail nodes is much easier than turning tail nodes into head nodes by adding edges. Adding edges is super hard because it's link prediction.
Because I think this problem is related to the problem of heavy tail problem or long tail problem.
Yeah.
But in the long tail or heavy tail problem, they just want to throw out this heavy tail.
Yeah.
But here, they want to think this heavy tail data or the hit node is very important.
Yeah.
Like that.
Yes, we don't throw the long tail data. Instead, we want to improve the performance on the long tail data because improving that performance is really important. A lot of in Amazon, a lot of users are new users, and we don't want to throw them away. We want to give a best recommendation to those new users so that we can gain those trust, or we can engage that into them. So, thanks, guys.
There's a question in the chat window.
Okay,
I think we missed one question half an hour before.
I think also we are running out of time. I don't know.
It's fine.
Can you
For the first question, the assumption was less than 10 colors.
less than 10
So
colors.
that's the answer.
Can you answer the intuition behind the random you can improve the overall performance in getting worse in some? Okay, that's a great question. So I think the question is monotonically, I guess it kind of means that like across node degrees, we are improving over the base GNN. And I guess, okay, my intuition is that performing well on the head nodes is so easy that if once we perform well on the first stage, it's really hard to forget. And on the performing well on the tail node is so hard. So and even performing well on the head nodes have good effect on the head nodes because by performing well, by doing this drop edge training, we are kind of inject noise on the embedding, which kind of improve the performance even on the head nodes. For example, if you think about the mean aggregation here, by dropping two nodes, we are having more noisier embedding. We're still trying to use this noisy embedding to perform well. And this kind of training may improve the performance on the head nodes, right? By kind of inject some noise into the embedding and still make it perform well. It's sometimes helpful in machine learning. So I think that's why my intuition is that performing well on the head node is so easy. What's hard is the performing well on the tail nodes. That's why we improve on the tail nodes, but doesn't really lose at all on the head nodes. And I think I need to run the rest of the presentation really quickly. So the part 3, so far we talk about understanding, improving the performance of the GNN. Finally, I'm going to develop the benchmark datasets for measuring the performance of the graph neural network. So why we need the benchmark? Because we want to engage the community towards improving the performance of the graph neural networks. And historically, this challenging benchmarks have really driven methodological innovations like ImageNet. The performance on the ImageNet has been improved dramatically over time, and we see a lot of interesting methods like CNN, deeper CNN, and the vision transformer. A variety of methods have been developed to improve the performance. So I think having common benchmark in the graph neural network domain is also help us achieve the similar thing. That's in ImageNet. The issue, however, if you look at the existing graph benchmark, there are issues that I mentioned before. The datasets are too small, and they're also unrealistic in the sense that the features are not realistic. For example, there's no edge features provided for molecules, no node features provided for link prediction. So a lot of the graphs datasets are just so simplistic and not reflect the real world use case. And another thing is probably interested many of you, which is the distribution shift. Basically, a lot of our common benchmark just split the data randomly and follows conventional randomly. While in practice, we need to deal with the distribution shift. So to tackle this problem, in May 2020, we introduced this open graph benchmark, or OGB in short, which is a realistic and diverse benchmark datasets for graph machine learning. And we designed OGB datasets to be diverse to reflect the variety of practical use cases. So we are diverse in terms of task categories, domains and the scales. In terms of task category, we included the 3 kind of a core graph machine learning tasks: prediction at the level of node, prediction at the level of link, basically pair of nodes, and the prediction at the level of the entire graph. In terms of dataset scales, we prepared datasets with a small and medium and large scale graphs, and these small datasets are useful for quick methodological, quick iteration of different ideas, while medium and large graphs really reflect the real world kind of challenges of applying graph ML to large scale graphs. And in terms of domains, we have a graph from a natural science domain, social information network, knowledge graph, computer code, and we try to provide really realistic node, edge, and graph features on each of these graphs data sets. And also we consider this domain specific data split for different applications. For example, for link prediction, we split the edges according to time. So that we simulate this realistic prediction scenario. We given links edges up until a certain timestamp predict the future. So we kind of give this domain specific data split. And this diversity in the different application domains really is reflected in the different graph statistics. Some graphs are really dense, others are really clustered, others have a large diameters. And having this diverse graphs datasets allows us to evaluate the GNN in a holistic manner. And in total, OGB Open Graph Benchmark includes 15 datasets from diverse domains and tasks. So the impact of OGB has been really huge. Many methods have been developed on our datasets, over 450 leaderboard submissions. So we have public leaderboard, and a lot of submissions have been made. Drastically accuracy improvement on many datasets have been achieved. And here I'm showing you the accuracy improvement on the 2 of our datasets, and you can see some kind of similar trend as the ImageNet curve. Over time, we have a better methods being developed to achieve better and better performance. We're really excited about this. So I'm going to summarize the trends that we've seen in this OGB datasets. So really, because of the diversity of the dataset, we really find different GNNs. The GNN are really optimized for each dataset to achieve the best results, and the different models hyperparameters are used to achieve the optimal performance on the different datasets. And this is kind of a bit different from what we wanted initially. We thought there's a single kind of a unified graph foundation model or something like that that can achieve good performance across all the datasets, but that doesn't look like seem to be true. And that's probably because of the nature of this graph machine learning, where it's just the graphs are so diverse, application target labels are too diverse that it's really hard to develop single model that achieves good performance on all the datasets. Still, there are some common trends. For example, for graph classification problem, we find it useful to kind of augment the graph so that the GNN can kind of look at the global information at each round of neighbor aggregation. Some techniques being developed are virtual nodes that are connected to all the nodes in the graph. So this kind of connects to your question. So this actually doesn't give us added expressiveness, but it's kind of good because these nodes allow us to kind of exchange information globally. Doesn't increase the expressiveness, but somehow improves the generalization power. And
I was thinking that if the number of layers, which is the number of passing messages, right, are the same, then I think it should increase the expressiveness.
I kind of thought about this problem, but we can discuss more. But I don't think adding virtual nodes gives you more expressive here that can distinguish more graphs. But it does gives you good generalization performance. And some methods even connect all the nodes in the graph, but on the edge feature they added some positional encoding to capture the relative nodes position within the graph. Okay, so we also went further to kind of organize the graph machine learning challenge. So we we thought, OGBs is really great, but still the scale of the OGB is, it doesn't reflect the really, industrial scale of graphs that we find in many applications. So we provided this extremely large graph data sets up to 240 billion nodes, and I think it's around the 300 or 400 gigabytes of data that we distributed, and we organized this KDD Cup and NeurIPS competition around this data sets, and we've seen, huge improvement on our data sets as well. So, and for all the details, please check out our webpage. You can find more details here. So in summary, we present this OGB for benchmarking GNN's predictive performance. And now OGB is really widely adopted by the community to advance the predictive power of a graph neural network. So in conclusion, in this talk, I aim to build the powerful graph neural networks to make prediction over graph structure data. So in part one, we first aim to provide understanding of the predictive power of GNN. We analyze the expressiveness and design GNN that are maximally expressive. Then we aim to improve the performance of GNN under limited data scenario. We consider this limited label data, limited edge connectivity scenario. And finally, we step back and think about how can we benchmark the predictive GNN, power of GNN, so to engage the community into building more better GNN. So we present this OGB. I'm going to just briefly talk about future challenges. I think the most exciting challenge is the large-scale graph machine learning, and especially I think so far OGB, this large-scale challenge focuses purely on accuracy, but we've already seen having this 2 competitions in a row. We've already seen a lot of methodological innovation, but what's kind of missing is the effort from the system side. We want to train large graph to require accuracy with limited budget. And this is, we don't want to train model for a few days to get one result, but ideally we want to, train large model within a few hours. And that I think is really exciting next challenge for us. It's kind of analogous to the downbench that Stanford is developing, and a lot series of work on ImageNet training in minutes. I think it's really exciting if we can train GNN on 240 million graph in minutes. That'll be super exciting. And I think it's not only about the machine learning, but really requires a system networks. Another thing that I found interesting is this AutoML for graphs. In OGB, we basically find that the different graphs are so different that the optimal hyperparameter models should be kind of specifically selected for each data set. And we did want to build this AutoML system that produce good GNN model given fixed budget, and that will really democratize the GNN model to a wider audience. And with that, I want to acknowledge all my co-authors and collaborators. Thank you so much.
Thank you very much. So we have one more question from the window some time ago.
Is there any study on the influence of improving different proportion? Yeah, that's a great question. Certainly, some edges are more influential than others. I think there are some work on adversarial attack on graphs where they think about not just removing, but how to add edges so that the prediction of GNN is maximally changed. And yeah, there's certainly such work.
I have a question.
Yes.
So I wanted to ask about the computational issues, but at the end you had some future work there. But suppose you have a huge graph, then of course the computation is quite challenging. Then another way, so you have many small graphs.
Yes.
Still, this is also computationally quite challenging.
Yes.
So can you identify any difference between these two cases?
Yeah, definitely. So many small graphs, I would say. So I in my opinion, I think large graph is more challenging than small graphs because the way we train up GNN or large graph is first by decomposing it into small graphs, doing subgraphs,
I see.
and then, for example, like for each.
Do you do that? In,
Yeah. Like we, for example, we kind of sample small number of neighbors
Oh,
that
yeah.
generate the embedding. So we kind of actually in practice we generate isolate graph and then generate the embedding. That I think is more challenging. And actually, what's surprising here is, generating the subgraph is actually the most expensive part is retrieving the feature, because to generate one node embedding, you need to gather, let's say, 1,000 node embedding, and retrieving that 1,000 node embedding from 1 terabytes of memory is just super the most expensive part. Not really the GNN part. This computation part is not super expensive, but this system side, how to do efficient I/O is the most expensive part.
Another question is about interpretability.
Yes.
Because extracting features from graphs is kind of ultimate question. Can we learn from learn GNN that this kind of feature is useful for classifying something?
Yes, that's a great question. I think there are some work on counterfactual explanation of GNN, basically meaning that what if given GNN makes this positive prediction. Counterfactual means that you kind of remove some pages and ask counterfactual question, and they basically ask what's the kind of smallest functional group that can be they basically try to mask out as much graph as large portion of the graph as possible, but still retain the positive prediction, and they basically give that the final remaining portion as explanation.
Can someone read the trained GNN
Yes.
to understand like what kind of feature was actually useful for?
Right. So by that, for example, for chemistry, they can read this functional group is kind of responsible for this positive.
Is it similar to kind of feature selection?
It's similar to feature selection.
But they are not independent but connected to the graph.
Yes.
Quite interesting.
Yes.
Other questions?
Excuse me, I have one more question.
Yes.
So I'm wondering if there are some trade-off between expressive power of GNN and the generalization abilities. Actually, input gene is actually more expressive than GCN. So for example, for some easy data, will GCN has some more generalization power?
Yes, definitely. There is a trade-off.
Yeah.
So I talk about the guideline. When the features are not rich,
Yeah.
I guess the expressiveness is important. When features are rich,
Yeah.
then it's all about
Yeah.
generalization.
Yeah, I'm really interested in this. So is there any measure for the richness of the feature? So
A measure?
Yeah, a measure. So you can
Right.
calculate. So before we just train the model, we can calculate a measure, an index.
Yeah.
And to decide whether we use a complex model or a simple model.
Right. I think that's I don't know any work that that measure this complexity, but it's not just the function of this input feature, but also target label, right? How complex target, if your target labels are smooth over the graph, maybe all you need is GCN, just doing some average. But if your output is really complex function of a graph, maybe you need a more complex. So it's my point is that it's not just the input feature, it's actually also output label that you want to.
Two questions in the chat window.
Do you consider about the sample bias issue? Was sample bias, which method? I'm not sure. So
Microphone.
maybe I can switch to the second one. It seems that GNN is more difficult to parallelize compared. Yeah, so GNN is more difficult to parallelize. I see. Yeah, I think GNN can be tricky because normal MLP, you just have a matrix multiplication. GNN, you need to have a sparse matrix and dense matrix. So that part is probably slower on GPU. But I believe there's a lot of effort from hardware community to overcome the issue, to basically make this sparse matrix multiplication faster. Does this answer your question? And for sample bias,
We need a bit more clarification on the question. So, which method and what kind of sample bias are you talking about?
yes.
Can you train on subgraphs in a way that the model generalized to the whole graph, size generalization?
That's a great question. I think that's challenging for
What
now.
assumptions do we need?
I think then the most important one, like part is the general architecture. Yeah, like if you use the sum versus mean versus median versus different aggregation function, really have different extrapolation behavior. For example, if you start to use sum aggregation, then you have a when you do size extrapolation, your output value will be larger for graph with larger size, right? While for mean aggregation, it's kind of independent of your size. So how you want to extrapolate to a graph with larger size, then that's it's kind of now it's really design of aggregation function or GNN model architecture. How you need to really think carefully about how you want to extrapolate to design a GNN.
I was wondering something similar about like the tailhead, the augmentation method you presented earlier. And what's the aggregation function used there? Is it like mean aggregation? Because I feel like if it's like also like different aggregation functions should be more effective or like
Yes.
less affected by that.
So that's a great question. So in here, I tried the graph stage and GCN. Later, I was doing rebuttal, and I tried 3 more architecture. I tried max, I tried sum, and I tried attention.
Can you remind me what graph stage and GCN use?
Oh, they are kind of using mean, both mean.
Okay.
GCN is kind of using a fancier version of mean, but yeah. And what I find is that the sum aggregation is trickier. Max aggregation, attention, our method is working fine. But sum aggregation, I guess, it's trickier because the distribution between head nodes and the tail nodes, the embeddings will be so different.
Thanks.
I think some researchers use multiple aggregators.
Yeah.
What do you think about it? Like if they have the same expressive power,
Yeah.
then what to make a difference?
Yeah, I think multiple aggregation is very useful. I think what prevents people from using it is slow. If you use 5 aggregation, currently there's no GPU kernel for parallelizing that, so it's 5 times slower. I think it's basically useful, but I think we also tried it, but it's slower if you use more and more aggregation.
Oh, I see.
Because but I think that's not an essential bottleneck. That should be resolved with a better kernel, GPU kernel.
Yeah, I think in
But-
this year's LOG, there's something very like a learned aggregator.
Yeah.
How do you think about this?
Yeah, I think that's super useful because you even want to learn which one to use, right? So yeah, I think it's a useful direction.
Nice. Thank you.
I have a question. It's about the trade-off between the expressivity and the generalization.
Yes.
In deep neural network, we find an interesting trend termed double descent. When we enlarge the capacity of deep neural network, the test error decrease first,
Yes.
then increase, but finally it decrease.
Mhm.
So in the graph neural network, do we observe similar trend?
I see.
Or so because you you just talk about that sometimes there's a trade-off.
Yeah.
But if we have much more expressive graph neural network, can we achieve both the expressivity and the generalization at the same time?
Right. I think I don't know what double descent behavior in GNN, but certainly like this behavior where in GNN, we don't observe this severe overfitting as you over-parameterize the model. It's not like you have a larger and larger model and I think you usually saturate your generalization will saturate at some point. It won't be bad. So I think I'm not sure about double descent behavior, but I think even in GNN over-parameterization. Yeah. That's my impression.
So is there any like a contrastive learning method to do the data augmentation?
Yeah. So people kind of drop edges, drop nodes, and try to make the embedding of the augmented graph similar. That definitely exists. Yeah.
All right, then, so thank you very much. So please join me to thank Wafer for the great talk. Thank you.